Good morning, and sorry about the slight late start. This morning things just did not want to go my way. You know, one of those mornings. Does everybody have got the slides? Where are the spare ones? Okay. And is the register going around as well? Lovely. Okay, so this is the last workshop for the term. That's better. And what we're going to do today is the multivariable optimization, and it's going to cover both the unconstrained and constrained. So in a little bit more details, at the very beginning, I'd like to go through the single variable optimization because obviously we're building on it. And recently I've seen a few students who get a little bit still confused about what's the difference between point of inflections and how to look for it. So I just like to draw your attention to that again. Have I turned my thingy on? Yeah. Sorry. Then we're going to go into how to do the unconstrained optimization for bivariate functions. Then we look at constrained optimization, the Lagrange method, because the substitution method is not very used, so I don't think we should spend any time on it. And at the very end of the lesson, we're going to look at Marshallian demand functions and Hicksian demand functions, and do a little bit of work on indirect utility and expenditure. I hope that's fine with everyone, and hopefully we'll have some time at the end for specific questions. Right, so single variable optimization. First of all, you need to find the stationary points, and you know the stationary points are where the first order derivative is equal to 0. So you differentiate the function once, set that equal to 0, and you solve the equation. With that, you find the possible points of from those you find all the stationary points, which can be minimum, maximum, or stationary point of inflection. So that is where these possible things are, and you need the second order condition for distinguish between those three different things. So you find the second derivative of the same function, and for x you substitute the value that you found in here, and if that specific value gives you positive, you found a minimum. If that substituted value gives you a negative value, you found a maximum. If that's equal to 0 at the second order condition, you found a possible point of inflection, and you have to check for the second order condition to find if it's indeed a point of inflection, or you have to do something else. So if the third order derivative is not 0 at that specific point where the second order derivative was 0, you found a point of inflection, and this one is a stationary point of inflection because we identified x from this, and that's always a stationary point. If the third order condition at this specific point where the second was 0, the third is still 0, then you have to go for the nth test because it can still turn out to be minimum or maximum. I know a lot of things going on in there. Now, what does the nth test do? Well, you basically just keep differentiating the function until you end up with a non-zero derivative at the specific points that you are interested in. If the number of derivatives that you had to do was even, and the value is positive or negative, you found a minimum or a maximum. But the number of derivatives, if that was odd, you found a point of inflection. Okay, again, it's possibly a stationary point of inflection because you started from 0 at the first derivative. For the non-stationary point of inflections, the first order derivative is non-zero, because obviously all stationary points, the first order derivative is 0. For something to be non-stationary, that means the first derivative can't be equal to 0. Okay, just spend a couple of more minutes on how to check for points of inflections. Okay? Stationary points of inflections you will always come up with starting from the first order conditions, because those are also stationary points. But what you need to know about points of inflections is that the second order derivative at the specific point is always 0 and the third order is not 0, or the odd is not 0. Stationary when the first order derivative is 0, and non-stationary when the first order derivative is not 0. So as I mentioned, starting with the first order condition, you will always find the stationary point of inflections. But how do you check for non-stationary point of inflections? You look at the second order derivative, set that equal to 0, see if you can identify any other axis solving the equation that is different from the first order condition. That is your point of inflection, non-stationary point of inflection candidate. Then you check for the third order condition at that point, and if that is non-zero, you find a non-stationary point of inflection. Any questions? There's a lot of things in there. And it's been quite some time now, hasn't it?
I always forget to go back and check the other ones.
The non-stationaries. It's just somehow you have to make sure that you check for all minimums and maximums, and stationary point of inflection always come from the first order derivative, so you don't have to do anything else. But the kind of outlier, the one that you have to keep in mind and always go back for it, is the non-stationary. So just remember there is an extra step to check for the non-stationary.
When you say minimum, maximum, or stationary?
Minimum, maximum, or stationary point of inflection. Okay? Because all three is stationary points.
You can't have a point of inflection and or a maximum. You can only have like one of the others.
Yes, so at one specific point, it's either minimum, maximum, or stationary point of inflection. It can be a combination of these things.
So both points of inflection, the stationary and non-stationary one won't be 0 at the third derivative.
Either the third derivative won't be 0, or the odd number of derivative if you needed to go for the nth test. But they both 0 at the second.
Yeah.
So you only just do two things, but so you, the first thing you do is set the first order conditions to 0.
Yep.
And then everything spills out from that.
Yes.
You could get a point of inflection
Yep.
there, if you get the 0 in the second one. And then you've got to remember after that to set the second order condition to 0
Exactly.
to hoover up anything else.
Exactly. Exactly. So the extra step is to look for where the second order condition is equal to 0, and if that's going to give you anything new, and if that's giving you anything new, that is a non-stationary point of inflection, as long as the third order derivative is also non-zero at that point.
If third order is 0, does that mean it just sort of...
If the third order is 0, you have to go into the nth test and investigate further, because that might be something else. But because it's I mean, usually the nth test only comes if the first, second, third, the rest of them starts to become all 0. Yes?
I remember we were told by Katja in one of the classes that if we take the second derivative, set it equal to 0,
Yeah.
take those values out of that equation and put them back into the first derivative, it determines whether it's 0 or not 0, will give us whether it's stationary or non-stationary.
Yes, that is the distinction in between them, but you mustn't forget that just by setting the second order equal to 0, that's not necessarily yielding you always the points of inflections, because you have to check for the third derivative not 0 as well, because there are two conditions in there.
So let's say if it's not 0 and we put
Yeah,
it back
exactly.
to the first, we'll
Yes, but
verify.
do you always have to put it back to the first order derivative to check if it's stationary or non-stationary? Because by this stage you already went through all the first order conditions. So you already identified what are all those different stationary points turned out to be. So from that condition you can only have those stationary points. So in most cases, when you look at the second being equal to 0 and identify a new point, that is most likely going to turn out to be non-stationary. Obviously, you want to double check, but you can be quite confident that it will be a non-stationary. Because you can always make a mistake in the first place, solving your first order condition. Okay, any more questions? Yeah.
And test when, I mean, during the exam, if you do first,
Yeah, set it equal to 0.
third one, you waste time. So is
The AND test is necessary because in those cases, the second, third order derivatives turning out to be 0 at those specific points, and you still don't know what kind of point you
you
have.
have to do that before you end the end test.
The AND test itself is basically comes into play when you found the first order, you've set the first order condition, identified x's, then you look at the second order condition and it gives you 0 at that specific point. You look at the third order condition and that still gives you 0 at that specific point. This is when you move into the AND test. If you find anything non-zero before, then you don't have to go into the AND test. But if the third is still 0, that's when you keep carrying on. Okay? Thankfully, there's not so many steps in the multivariable version. So, when we talk about bivariate functions or multivariate functions, what do we mean by them?
It's got more than just x.
Exactly. So you start to have more variables than just one. So just like real life, it gets messy. So again, you can have minimums, maximums, and saddle points. Okay. So we moved away from the name of inflection point, but the saddle point is very much same thing. It's neither minimum nor maximum, but the first order derivatives would be 0 at that point. So it's very similar, but because we are now in more than 2 dimensions, we named it slightly differently. Okay? And obviously minimums and maximums are, I'm hoping obvious what they are. So, for the unconstrained optimization, again, first order conditions, very much the same, but because we have now more than one variables, we have to set every single one of those first order partial derivatives being equal to 0. So the extra difficulty here comes from the fact that now you have to solve systems of equations rather than just a simple equation. And from then on, you can identify the values of x and corresponding y's. So now you're working with pairs of numbers. Because don't forget that now you are in most cases, now you are in 3 dimensions. So here are your coordinate plane. So you're talking about x and y coordinates. And here is your function, which is again another plane. So when you identify x and y, what you actually do, you identify one specific point down on the plane, and you're trying to find out that the corresponding value up on the function plane, what is that on the surface? What is that? Is a minimum? Sorry, is a maximum? Is a minimum? Or is one of those? I can't do a saddle point in here, unfortunately. But you know, one of those saddle-looking things, which is neither minimum nor maximum. Okay, so be careful that you need to identify corresponding pairs of x and y, not just x and y randomly. They have to be paired together. And then, if the second order partial derivatives are both positive and their multiple is bigger than the cross partial square, you found a minimum. If they are both negative and the multiple of the second orders bigger than the cross partial square, you found a maximum. Pay attention to here that this is exactly the same condition for both of them. Okay? Now, you found a saddle point if this condition switches.
With the first one. So one's going one way, one's going the other way, and it's...
No, these two going exactly the same way. If it switches, that's a saddle point. So you can find, in many cases, these two being different signs is a telltale sign of that you find a saddle point, because obviously positive times negative will always be smaller than a squared number. So that's always going to turn out to be a saddle point, but that's not the only cases of saddle points, because you can have fxx and fyy being equal to both of them, and fxy being 3, and then they are all the same sign, but 2 times 3 is 4, y 3 squared is 9. So saddle point is not only when these two are alternating in sign, they can be same in sign and still saddle point. So be careful there. And if they turn out to be equal to each other, then the test failed, and you would need to do some further investigations, which is not part of this course, thankfully, because optimization theory is not quite straightforward. Okay, so anybody who is going, hello, slides are here. So if anybody is interested going into masters, you're going to go into more details there.
So, quick example.
Yep.
Right? Let's say we have the second order partials like 4 and minus 8. So one's greater than 0, one's less than 0.
Yes?
If that's less than the cross partial squared, it's a saddle point.
It's always going to be less than the cross partial squared, simply because if one is positive, the other is negative, the multiple is negative. And the cross partial is squared, regardless if that's positive or negative, that's always going to be positive. So that's always a saddle point. What I was trying to explain is that's not the only case when you end up with saddle point. That is going to be saddle point all the time, but you can find saddle points elsewhere. Okay, so just be careful. Just because something is both positive and both negative, that doesn't necessarily going to give you minimums or maximums. You always have to check for this, because in some cases it might still turn out to be a saddle point.
Is it just impossible to have an inflection point in a sort of three-dimensional space like that?
What do you mean inflection point?
As in, like, we can find inflection points in a single variable function. And I'm just trying to visualize why we don't have inflection points when we now have.
What do you mean by inflection point?
As in, like, it's turning the second derivative is.
Yes. So it's something that is neither minimum nor maximum, but the first order derivatives are 0 there.
Yeah.
It's the same as the saddle point.
That's basically just what the saddle point is.
Yes, the saddle point is the next dimension equivalent of the, and I think it's just named saddle point because when you graph it, it looks like a saddle.
Right, okay.
Because it kind of goes in one way and then comes in another way, sort of funny looking thing. And it was just obvious to name it saddle rather than inflection point.
Yeah.
Visually more telling. Because, I mean, inflection point, okay. How can you vision that?
Yeah, I mean, as a line, I can vision.
Yes,
it.
exactly.
Yeah.
It's the surface.
Yes, exactly. Something funny looking thing. So I think it's just as the choice of the name, but the concept itself is pretty much the same. Just be careful that once you're in more than two dimension, it's a slightly different name. But conceptually, it's pretty much the same. Neither minimum nor maximum, but the first order derivative is still 0. Okay. So, you tell me now what we need to do. So let's look at A. So what will be the first step?
Find the first.
So we need to find the first of the partials. So you need to find fx, fy. Thankfully, we only got 2 variables. Okay, so what is the first order partial with respect to x?
Minus 6x.
And that has to be equal to 0. And the first order partial with respect to y is? And that's equal to 0 again. So it's a system of equation, thankfully a very simple one. So I know that 24 has to be equal to 6x. So 4 have to be equal to x. 8 has to be equal to 4y, so 2 has to be equal to y. So now I've got my stationary turning points. X star equals 4, y star equals 2. Next step. Second order condition. So what do I need to find for the second orders? Okay, so I go back to fxx. What will be fyy? So they're both negative. And if I go back to fxy, okay, so the last thing I need to check is minus 6 times minus 4, is that bigger than 0 squared? And yes, so the last condition of the second orders also hold. So what have I found? Maximum, at x equals 4, y equals 2. Alternatively, I can write it this way, maximum at 4, 2, because then I know that I am exactly at that point in the coordinate plane, the xy plane. Okay? And I wish you have these simple questions in the test, although you probably won't. Okay, so that was A. Now let's look at B. Okay, so same drill. First order condition, the two partial derivatives with respect to x and y. So what's the first, what is the partial derivative with respect to x?
2x plus 3y minus 4.
And that has to be equal to 0. Look at the same function again and give me the derivative with respect to y. Equal to 0. Okay? Now what I'm going to do now, solve this system of equation. It's not as simple as the previous one was. So I'm going to say 2x plus 3y equals to 12 and 3x plus 2y equals to 14. So how do you solve this type of equations? Yes? How?
We multiply them so that you get the same value.
Yes, so you can do the elimination method, basically multiplying one or both of the equation until you have got either x or y having the same coefficients. Or you can use the substitution method, saying express x or y from one of them and substitute back into the other. In this specific case, I think it would be easier if I did the elimination method, because then I can avoid working with fractions. So, doesn't matter which one I'm choosing, x or y. It's just going to make a difference which variable I'm going to identify first. So I'm going to make x's having the same coefficients. So I'm going to have to multiply this equation by 3 and this equation by 2. So that's going to give me 6x plus 9y being equal to 36 and 6x plus 4y being equal to 28. So what you're going to do next? What is the next in line for solving this kind of equations? Subtract them. And in this case, I would subtract the bottom one from the top one, because the top one has got bigger values for y and the number. So I would end up with non-negative values. So 6x minus 6x0, that was the whole point of the elimination. 9y minus 4y gives me 5y. And 36 minus 28, what does it give me? 18?
8.
Oh yeah, 8, of course. So then y is equal to 8 over 5, which is 1.6. Okay, so found y. What I'm going to do next? Substitute back into either of the original ones. Again, doesn't really matter. I'm going to go for the first one. So 2x plus 3 times 1.6 have to be equal to 12. So 2x have to be equal to 4.8. Is that 4.8?
Yeah.
So 12 minus 4.8. Somebody calculate that for me, please. And x, therefore, half of that, which should be 3.6. I'm assuming we've done the calculations correctly here, but you ought to do it with the calculator, especially in the exam, because you'll be nervous enough to make silly calculation mistakes. Make sure that you use the calculator and you don't mess up your numbers. So my x star now is 3.6 and my y star is 1.6. Assuming we've done everything correct. What's the next step? Second order condition. So I need fxx, I need fyy, and I need the cross partials as well. So fxx is 2, fyy is 2, both of them are positive. And what is fxy? Okay, so check the last condition. fxx is 2, fyy is 2, and fxy is 3 squared. So that is 4 less than 9. What does it tell me? Saddle point. Okay? So this is one of those examples when both of yours are positive, so you think you're on your way to finding a minimum, but by looking at the last condition, it actually turns out to be a saddle point. Okay? So I'm going to write in here saddle point at 3.6 and 1.6. And again, we didn't have to substitute anything into here because these are independent of x and y. Pardon?
Can you explain a bit more on this point? Because I know that sometimes we have to substitute if we go.
Yes, if it's still got x's, you have to substitute. But this one doesn't have any x or y variables in here, which means that every single point on the function, the second order derivatives with respect to x and the second order derivative with respect to y, at every single point will be positive 2. And the cross partial will be positive 3 at every single point on the function. Where is my register? And who else has to sign it? Okay. Any more questions about this particular one? Okay, so as you can see, the bivariate cases, the multivariable ones, are slightly simpler in the sense that you don't have to look at so many conditions. You don't have to go back and check for another type of thing. But the equations themselves to solve can be a little bit trickier, especially once you start to do parametric versions. So the last example of the generic ones. So again, first order conditions. Find the first order derivative with respect to x and with respect to y. So that will be
3x minus 2.
and that has to be equal to 0. And with respect to y is and that's again have to be equal to 0. So what do we have here is 3x squared have to be equal to 2 and 3y squared have to be equal to 5. That tells me that x squared have to be equal to 2/3, which means x have to be equal to plus or minus root 2/3. Okay, generic solution, you can have positive and negative values. This is not like prices and quantities when you can only have the positive ones. So be aware that for the generic ones you need to have both of them. And y squared equals 5/3. So y similarly will be positive negative root of 5/3. Now unfortunately, this doesn't tell me any relationship between x and y. So what's going to happen now? I have to pair them up with all different possible combinations. Okay? So I identified quite a few points then. So what are the different, I'm going to write them here so I have enough space to do the calculations over there. So what are the possible combinations? Well, both of them can be positive. So I can have the root, 2/3 and root 5/3. Then the first can be negative, the second still positive, then the first positive, the second negative, and both of them negative. Okay, so these are all the possible point combinations that I can get out from there. If x would depend or y would depend on the other one, then obviously that would be slightly different. So that was the first of the conditions. So we identified 4 different points, and now we need to classify every single one of them. So, second order condition, I need the cross partials. Sorry, I need the second order partials and I need the cross partial. So what is fxx? fyy and fxy. Okay, now both of them depend on x and y. So first depends on x, the second depends on y. So we now need to substitute back. So the first pair combinations, then fxx will be equal to 6 times root 2/3, which is positive. fyy will be 6 times root 5/3, which is positive. And if I multiply these two together, 6 times 6 gives me 36. And I'm not going to calculate too much in here because I know that this is definitely going to be bigger than 0 squared. So what have I found? Okay, so minimum, maybe shouldn't write here. Minimum at root 2/3 and root 5/3. So this one was a minimum. Okay, so that was the first point. What I need to do then, I check for the second point. Okay, can I rub the board off? I'm going to be lazy. I'm just going to rub this part off because I'm going to need these conditions again. So, when we're looking at minus root 2/3 and positive root 5/3, then what can I say about fxx? That will be 6 times negative root 2/3, which is negative, and fyy will be 6 times positive root 5/3, which is positive. fxy is still 0, because that doesn't depend on either x or y. So what can I say about the last condition? So 6 times 6 again gives me 36, but one is negative, the other is positive, so I'm going to end up with negative 36 times root 2/3 root 5/3, which is definitely smaller than 0. So I found the saddle point here.
So Ava, can you generally stop when when the signs don't match up? Yeah, of course you can every time, right?
Pardon?
You can, you don't need to go any further. If fxx is negative and fyy is positive, then obviously that third order condition is going to be for a saddle point.
Yes. Yes. However, double check with Tony if he wants to see you spelling this one out. Okay? Because sometimes, I mean, the trouble with these written exams that you're not there to explain that you know what you're doing. So they can only judge you by what you've written down. And you can, if they sort of very cynical, they can say, oh, he just guessed and got lucky.
And fxy might not always be 0.
Well, yeah. In this specific case, obviously. But it depends on case and case. Okay, so that was the second point. So we found the saddle here. What's your feeling about this one? The next one. That's going to be a saddle again, but let's just make sure. So when the first one is positive and the second is negative, what's going to happen to fxx and fyy? This one's going to be the positive one, but this one's going to be now the negative one. So this would be positive, and this would be negative, but the multiple going to stay exactly the same, because positive times negative gives you the negative, and the number values are exactly the same. So we again found the saddle. And then we only got the last one now. Can I rub the board off? And the last one is when both of them are negative. So minus root 2/3 and minus root 5/3. Okay? So that will give me minus 6 times root 2/3, which is less than 0. And it gives you minus 6 times root 5/3, which is also less than 0. But fxy is still 0. So what's going to happen in this case? Negative times negative that is basically a positive number. So that's going to be definitely bigger than 0. So what is the last point? So this is a nice function. It delivers everything you can ever wish for. Okay? Any questions?
minimum, local maximum, or is it?
Well, to be on the safe side, you should always write local minimum and local maximum, because what I suspect is one of those surfaces that will go into infinity. So the global would be positive and negative infinities if you would have. The trouble with these things is that you can't visualize them, so you don't really know what's going on. So to be on the safe side, you could always just write local minimum and local maximum. You would need a little bit of further investigation to find out if they are actually global or not. What does Tony usually do in the lessons? Does he always write local? Yeah, always write local. Right, that's all nice and lovely with x's and y's, but that's not what you're here for, because you want to become economists. So you need to be able to apply these into the world of economics. So, a monopolist produces the same good for two plants, Q1 and Q2. These are the different cost functions. You've got the average revenue function, and you know that the total output is the sum of the two different outputs. Question 1, or A, find the profit maximizing level of output and prove they are a maximum. Then you need to find the output produced at each plant and the price at which these goods sell. And Tony usually quite kind, because he gives you sort of hints as to what to do. So as long as you follow the instructions he's giving you, when he's generous enough to give you the instructions, you'll be absolutely safe. So basically, first define total revenue, then subtract from that the total cost to get the profit expression in terms of Q1 and Q2, and then maximize. So, find the total revenue. So what do we know about the total revenue? Price times quantity. Luckily we got the price, which is 20 minus Q, and now we just need to multiply that by Q. So that is 20Q minus Q squared. Is that good enough for us as a profit function, as a total revenue function? Almost. We have to have it as a function of Q1 and Q2, because there are two outputs. So what I need to do now, substitute for Q as Q1 plus Q2. So that will be 20 times Q1 plus Q2 minus, oops, lowercase, not capital, Q1 plus Q2 squared. So the total revenue is 20Q1 plus 20Q2, Q1 plus Q2 squared, with a negative in front, will give me negative Q1 squared, negative 2 Q1 Q2, and negative Q2 squared. Okay, that is just finding the square of a sum, which is square of the first, double of the two multiplied together, and the square of the second. And because I had a negative in front, every single one of them will become negative. So that was the total cost. To find the profit, we also, that was the total revenue. To find the profit, we also need the total cost. So what will be the total cost?
C1 plus C2 is 5 plus 2Q1 plus 7 plus Q2 squared.
Okay, so we now got the total cost. So find the profit. That is total revenue minus total cost. So 20Q1, I'm just going to copy them and I deal with that in the next step. Plus 20Q2 minus Q1 squared minus 2Q1 Q2 minus Q2 squared. Take away the total cost, so take away every single term. None of them are positive. Sorry, all of them are positive. So when I'm taking them away, every single one of them will become negative. Actually, I can do 5 and 7 together. That gives me positive 12, so I need to take that away. That will be negative 12 minus 2Q1 and minus Q2 squared. So simplify this function a little bit. I've got 20Q1 and minus 2Q1. So that's going to give me 18Q1. I don't have any I don't have any other Q2. I don't have any other Q1 squared. I don't have any other double. But what I've got here is Q2 squares. That gives me 2 in total. And the minus 12. So that's the simplest form of the profit function, assuming I haven't made any calculation mistake. But that's why you are here, to check me. Okay, now how do we maximize it? Taking the derivatives. So I need again the first order conditions. So I need pi. So I need to differentiate the profit with respect to Q1. And I need to differentiate the profit with respect to Q2 as well. So the derivative with respect to Q1 is? And that has to be equal to 0. And with respect to Q2, and that again have to be equal to 0. So again, I'm going to write them here. So 18 equals 2Q1 plus 2Q2, and 20 equals 2Q1 plus 4Q2. So it's a system of equations again. What can you spot me about these two? They've got the same coefficient. Q1 have got the same coefficient in both of them, so I can subtract them. But what I would do now, instead of taking the bottom away from the top, I would take the top away from the bottom. I can do that as well. It doesn't matter which one I'm taking away from which one. The reason why I'm doing that, because I want to end up with positives. I don't like negatives. But it's your choice. So if you're just happy with taking away whichever way, go for it. So 20 minus 18 gives me positive 2. 2Q1 minus 2Q1 gives me 0. 4Q2 minus 2Q2 gives me 2Q2. So Q2 is 1. I'm going to write that here. And then what you're going to do next, substitute back into either of the original ones. Go with the top one, just as easy as the bottom one. I know that Q2 is 1 now. So 2 times 1 is 2. Take that away from 18 gives me 16. So 8 is Q1. Okay. Now, prove they are a maximum. Okay, because at the moment, what we've done now, we identified the stationary points. So these are possible maximum, but they can turn out to be minimum or saddle points as well. So you definitely don't want to go to your boss saying, oh, we have to produce that amount to maximize profit, and turns out that you actually identified minimums. I don't think you will have a long career in there. So go for the second order condition then. So what we need for that, we need pi 1, 1, we need pi 2, 2, and we also need the cross partials. So pi 1, 1 going to be pi 2, 2, and pi 1, 2 is minus 2 again. And what I need to check now is minus 2 times minus 4, is that bigger or smaller than minus 2 squared? So 2 times 4 is 8, and that is bigger than 4. Okay? That's 0. That's negative. That's negative. So indeed, these are maximums. So you can be happily presenting it. Okay? So output produced in each plant.
Is that just Q1?
Yeah. Yeah, tricky question, because you've already identified them. So you don't have to do anything else for
Coming
it.
back to this point of
Yeah.
the maximization.
Yeah.
So output will be maximum at Q1 is equal to 8 and Q2 is 1.
Not output will be maximum, profit will be maximum at these outputs. The profit will be maximum. Okay, and the price at which these goods will sell.
So B, yeah, B is just asking A again. No, we get the same answer.
Yeah.
Oh, that's easy.
But it's just sort of trying to sort of test if you understand what you actually identified mechanically, more or less, in the first question.
But for C, we don't have to put it into the price function to find the price?
What else can you do?
Yeah. That's all it is.
Okay.
We only find one price for that now.
Yes, and that's a little bit tricky because, you know, but because these are identical products, so the monopolist produces the same good from two plants. So it is the same good. So you're probably going to charge them at the same price. That's why I'm assuming there are no different price functions. Okay, so basically that is the answer for A and B. And C, I'm going to need some space. Is that all right if I rub the board off? So for C, that's probably the easiest of, well, not the easiest, but the second easiest of them all. So the price is equal to 20 minus Q. So that is equal to 20 minus 1 plus 8, which is, so what's the price? 11. Okay, and because we don't really know anything about these goods, we don't know if it's 11 pounds, 11 pence, or 11 millions. Okay? Last unconstrained optimization question. At least if I remember correctly.
Yeah, it is.
Okay. So I know profit function, and the question is, determine the firm's profit maximizing level of output and show it is a maximum.
P is price? Or
P is just a parameter. I don't really know anything about it, so is A. Okay? Now, what are K and L in? When you usually look at this kind of profit function, what sort of economical scenario comes into your mind? Capital and labor. So R and W are the individual prices. So R is the price for a unit of capital, and W is the price for a unit of labor. So P is some other kind of parameter in this specific case, and so is A. The question doesn't really give us anything about them, other than I think we can safely assume that they're both positive, although that should be again clarified. So next time I have to make a note for myself. Because otherwise it can be difficult to proving if it's a maximum or not. Okay. Right, so profit maximizing. So again, what is the drill? You need the first of the condition. So what are the variables in here out of those lot of letters? Because K and L are in the bracket behind pi. So that's telling me that those are my variables. So I need to take the first order derivative with respect to K and the first order derivative with respect to L of that profit function. Okay, so what's the first order derivative with respect to K?
1/3 AK to the minus 2/3 minus R.
And that has to be equal to 0. And with respect to L, and minus W, and that has to be equal to 0. So because both of them are 1/3, I don't really have to think much about it, just switching the powers. So how do you generally solve these equations? I can't divide just yet. I need to put R and W to the other side. So 1/3 P A K equals R, and 1/3 P A K to the 1/3 L to the minus 2/3 have to be equal to W, and now I can divide them. So over so conveniently I can cancel out the third, I can cancel out the P, and I can cancel out the A. So what are going to be the powers? What is the power of K? K is to the minus 1. What's the power of L? Positive 1. And that has to be equal R over W. Now knowing that K is power of negative 1, that is basically L over K being equals to R over W. So L is R over W K. What now? Exactly. So what I've got here now, I expressed L as a function of K, but I still don't know what L is in the expressed as the parameters. So I have to express it as function of P, A, R, and W instead of the other variable. So what I need to do now, I need to go back to one of the original ones and substitute back L into there. Again, the choice is yours. I probably will go back here, just because that's the top one. And here comes very handy your knowledge of powers or knowledge of indices. So first of all, I'm going to move these ones out of the way. So I'm going to multiply by 3 and divide them by P and A. So k to the minus 2/3. And I'm going to deal with that bracket in a minute. But so what I've got here is 3r over PA. And then what do I need to do with this bracket? Because all of them are to the same power, then I can raise them individually to the same power. So I would have r to the 1/3 over w to the 1/3 and k to the 1/3.
Sorry, could you explain that step one more time, please?
Okay, I multiply up by 3,
Yep.
divide them by P and A,
Yeah. All right. Okay.
and the bracket I just break it out to put everything to the same power.
Thank you.
Okay, so what power of k do I have here? K is to the minus 2/3 times k to the 1/3, positive 1/3. So that's all together will give me k to the minus 1/3. And again, I will need to remove these two. So I need to multiply up by w to the 1/3. So I've got 3r over PA. And I multiply up by the w to the 1/3 and divide them by r to the 1/3. Okay, so that's my k, but it's to the minus 1/3 and I want k to the power of 1. What do I need to do? Yes, why minus 3? Yes, so what you want here is k to have the power of 1. So what you need to think about it, what is the number you need to multiply minus 1/3 with to end up with a solution of 1, a result of 1. And minus 3 times negative 1/3 gives you the positive 1. And when you're multiplying the powers, that's when you're raising a power to a power. So basically what we're going to do here, we raise the whole equation or formula to the negative 3rd power. So raising this side to the negative 3rd, and all of this, so negative 1/3 times negative 3 gives me the positive 1, and that's going to give me the optimal value for k. And what happens in here? When I have a negative and a fraction inside, what's going to happen to my fraction? Flip or inverse, yes. So P and A and r to the 1/3 comes to the top, and 3r and w to the 1/3 comes down to the bottom, but I have not dealt with the power of 3 yet. I've only dealt with the negative part. So what I also have to deal with is the 3. So I have to raise everything inside the bracket to the 3rd power. So that's p cubed, a cubed, r to the 1/3 to the 3rd gives me r, 3 to the 3rd, r to the 3rd, and w to the 1/3 raised to the 3rd gives me just w. And what is the last thing I can see? r and r cubed, that can simplify down to r squared. So I'm going to write it here. So my k star is actually p cubed a cubed over 3 cubed times r squared w. So I've identified k star, but I also need L star. So what are you going to do?
Is that w squared though, on the right?
No, the r squared. the w was to the third, and you raise that to the w was to the 1/3, and you raise that to the third, that's just become w.
So it's r squared.
So it's r squared. The 3 has been cancelled and the 2 been put in there instead. So when you want to find L, where do you substitute back? Into here. Okay? Because that is a simpler way of finding L rather than going back to the original equations. You could find it there as well, but it's faster and simpler. So L is R over W times K, which was this. So what will be L star? So I can cancel them by R again. And W times W gives me W squared. So it's P cubed A cubed over 3 cubed R W squared. So I'll keep it here because I'm going to need it in a minute. Just spend a little bit of time on these two, and what can you spot me?
The only difference is one is r squared.
And the other one is w squared. Okay? So basically the squared switches in here. So there's kind of symmetry going on in here. So that was my first order condition, but I need to show it is a maximum. So I've identified again the optimal values, but I still don't know if it's minimum or maximum, so I need to show it's a minimum or a maximum. What? Is it clear, or have I lost you somewhere? Unfortunately, when there are too many letters lying around and flying around, it's...
But you divide the r because you multiply it by 3r.
This is r here, and that was r cubed here. So r...
Cancel that with the other two.
Yes. So instead of 3 now, here is just 2. Because it's r, so it's basically r over r, r, r. And then you can cancel that down. Okay? So how am I going to show that this is indeed a maximum?
And the whole second order thing.
Again, you're probably getting bored of it by now. I've got that there, so I don't need it. So, okay. So, what is the second order derivative with respect to k? With respect to L. And the cross partial will give me 1 over 9 times p a k to the minus 2/3 L to the minus 2/3. Okay? Now, what values can k and L take? They have to be positive. Okay? Now, even though it's a negative power, a positive number raised to any power will always be positive. So don't be misled by that k to the minus 5/3, because all that means that it's 1 over k to the 5th under the cube root. And because k is positive, its 5th power is positive, its 3rd root is positive, and 1 over a positive is still positive. Same goes for each of the cases where you have got negatives. So same goes for L, and same goes for these two, but it will be 1 over cube root of k squared and 1 over cube root of L squared. But they will always be positive. And we briefly mentioned at the beginning that P and A also have to be positive parameters. So that means this is definitely negative, both of them, because I have got minus 2 over 9 in here. The question is here now, is that comparison with the multiples and the cross partials, does that hold? Because I can still end up with an unfortunate saddle point in here. So what I need to do now is multiply these two together. See what that gives me. Negative times negative gives me positive. 2 times 2 is 4 over 81. P times P is P squared. A times A is A squared. K to the minus 5/3 times K to the 1/3. What does that gonna give me? Same case scenario for the L. Okay, that is the simplest I can get this. But now I need to compare that with the square of the cross. Okay, squaring everything inside the bracket, gonna give me 1 over 81, P squared, A squared. What will be the power of K?
4 and 3.
What?
4 and 3.
Yes, minus 4 over 3. And so for L, minus 4 over 3.
Is it not plus? Oh, no, it is plus. Yeah.
It was negative to start with. And when you're raising a power to a power, you just multiply the two numbers together. And negative times positive is still negative. Now, isn't that handy? K, same power, L, same power, A, same power, P, same power. So it all goes down to the difference between 1 over 81 and 4 over 81. Which one is bigger? That one. That was the multiple of the second order partials. That is bigger than the square of the cross. Because simply I know that 4 over 81 is bigger than 1 over 81. And everything else is exactly equal. Yes?
Why those powers over there, why they didn't change the sign? Minus square down or below over here. Why they didn't change their sign?
Okay.
Positive.
Negative 2/3 squared. Okay, so A to the negative 2/3 squared.
Oh, okay, that's not.
You're multiplying them together.
Okay.
Okay, so the base would change sign, the powers don't. So if it was minus A to the negative 2/3 squared, that would be A to the minus 4/3. So that would change the sign, but not the power.
Can you explain the second order derivative of this one?
Okay, so what I'm gonna go back into this one,
Yeah.
and I'm gonna differentiate it with respect to K. So I bring the 1/3 down, so that's how I'm gonna get the 1/9.
Yeah.
P and A doesn't change.
Yeah.
I have to take away 1 from the power of the K.
Yeah.
1/3 minus 1 is negative 2/3. And again, L's power doesn't change because I'm differentiating with respect to K now.
All right. Yeah.
And that was minus 2 over 3. Quite handy.
Why A and P has to be positive?
It wouldn't work otherwise. And
I mean, I understand that quantity cannot be negative. I understand
Yes.
K has cannot be negative.
If either of them would be negative, then this would not work. Because if P would be allowed to be negative, then you would have to think about, okay, what's going on if P is positive, what's going on if P is negative. Because if you're allowing P to be negative, then this would be positive, because negative times negative would give you positive, and positive times negative would give you negative altogether, so this condition would not hold, and it would not be a maximum.
So is the case to write an example A?
Yes. So that was sloppiness on my side, because if I don't write it out that P and A are positives, it would not work. They have to be positive, otherwise it doesn't work. Otherwise it's not a maximum, it's a saddle point. Okay? Happy to move on to constrained optimization? So, what's the difference between unconstrained and constrained optimization then? Yes.
You can't find the maximum wherever it is. You have to find the maximum subject to like a...
Exactly. So you're confining your function to a certain smaller interval out of the whole interval, and then you're finding those minimums and maximums within there. They're most likely not your overall minimums and maximums, but for whatever reason you don't have enough money, you have to find out what's the best you can bring out from your situation. Okay, everybody wants to have a Porsche, but most of us don't have the money for it. So that's kind of the... So you want a car, you can't afford a Porsche, what's the next best that you can go for, given how much money you've got? Silly example, but kind of. They are quite good cars. Okay, so you always have got your objective functions, you've got the constraint, and you build up the so-called Lagrangian function, which is the objective function plus this lambda times the constraint rearranged to number minus the constraint. And you've got again first order conditions, two variables plus the new variable, which is the lambda.
Sorry, just one more time. What's is V the constraint?
Yes, it's usually some number times, some number equals the function, like 34 equals 5x plus 4y.
Is that like the standard notation that people normally use? Because it looks different from the way Tony writes it out usually.
Oh.
This is just algebra problem.
In what way different?
It's not economic.
Or U.
Is that what you mean? In what way is it different? I don't understand.
When he does it, it's like utilities.
Yeah, usually writes just with algebra better. So this is like the general form.
You confuse me now, because I am almost 100% sure when I first wrote this slide up, I checked, and Tony's written notes were this in the hand.
I'm the one who's confused.
In the notes, because I'm usually working from his notes.
He doesn't do it in this right. It's like x plus y equals 34, but you can express it.
So this is the generic version. So basically this thing would be something like 34 equals 3x plus 4y. That would be your constant. That would be the s dot t dot. Right. Standard notation with parameters and variables rather than exact numbers. And I'm 100% sure that's the same in the notes. If not, let me know and then I'll change it around. Okay? So you've got an extra condition with the lambda there. So you need to again differentiate it. Why did we need to put this extra in here? What is this always going to give us back? It's the constraint. So the sole purpose of this Lagrangian multiplier and the extra condition is to make sure that the constraint stays in our system when we're doing the solution.
The way I think about it, I think about it is just it's like essentially just adding another variable, like adding another
Exactly.
another axis, like another set of.
Yes, so you're kind of adding other set of conditions, making sure that you within that remit, within that constraint. So you don't go out and identify something that's not in your reach. So solve for x and y, check second order condition and determine minimum, maximum and saddle point if any. How many of you have ever done the second order condition? How many of you know what the second order conditions are? Now, this is not something you need to know, but I just want to draw your attention to it. Don't falsely assume that the second order conditions are exactly the same as for the unconstrained optimization, because that is very easily done. Because now you have got a constraint, and again, this is only holding for two variable case with one constraint, and this is when optimization theory starts to become very messy and difficult to manage. As soon as you start to have more conditions, as soon as you start to have more variables, this is not the second order condition. This is specifically for two variables and one constraint. So you build up something called the bordered Hessian matrix. It's called the bordered Hessian because there are some extras in here. This original called the Hessian matrix, and if you find the determinant of this Hessian matrix, that is more or less what you're checking when you're looking for your original second order conditions with the unconstrained optimization. But basically, you find the maximum if this is positive, the determinant is positive, and you found the minimum if the determinant is negative. Okay, you have not talked about matrices yet. That's coming up in January. I just wanted to briefly show you to make sure that you don't falsely assume that it's the same conditions as would be for the unconstrained. It's more complicated. And as soon as you start to bring in more variables or more constraints, it just gets almost unmanageable. Okay? Right. So the point xy is the optimal solution for the constraint optimization. But what is the lambda? Lambda basically tells you that if we relax the constraint by a little, the optimal value will change by lambda. So it's either going to be bigger or smaller depending on the value of lambda. And by how much. Okay, again, these are all in the notes, and I'm pretty sure that Tony have mentioned them enough times. So let's look at the generic question. So what is going to be the first step? First, you need to write out the Lagrangian. So it's not going straight into differentiation and setting up the first of the conditions. First, you have to establish the Lagrangian function. So the Lagrangian function is always the objective function 6x squared plus 10y squared minus xy plus 30 plus lambda times what's going to go into the bracket? Okay. Strictly speaking, mathematically, it doesn't make any difference if you rearrange it to x plus y minus 34 or 34 minus x minus y. However, the reason why you always arrange it into number minus variables, because in economical situation, otherwise you would end up with prices and quantities being negative, which is obviously can't be right. So be careful that when you're rearranging it into zero, is always number minus the variables. And then, now you can set up your first order condition, which is so what is the first order derivative with respect to x of the Lagrangian? Minus lambda. That has to be equal to 0. So you mustn't forget that there is x and y also here, and that is basically lambda 31, lambda times 34, lambda times minus x, and lambda times minus y. And until you get used to being able to differentiate it with the bracket, you can always break that bracket up, and then you can see individually where the x and the y's are. So lambda y and then you can always just write down automatically the condition here, because that's the whole point. That is how lambda has been designed. That when you differentiate the whole Lagrangian with respect to lambda, just gives you back the constraint. So, what are you going to do now? Yeah, how?
12x minus y is equal to lambda, and 25 minus x is equal to lambda. 20x minus y is equal to 25 minus x.
Exactly. So you spot that because they are both equal to lambda, they have to be equal to each other. So that means that I now, from these two equations, I've got just one equation but without the lambda now. So out of the three, now I only have got two equations, but they only have got x and y in them. Okay, so what am I going to do with this one?
13x equals 21.
So x equals 21 over 13y. Substitute that back into here. So 34 equals 21 over 13y plus y. So 34 equals 21 over, oops, over 13y plus 13 over 13y. So 34 equals 21 plus 13 gives me the 34 over 13y. So I can multiply by the 13, divide them by the 34. So 13 is equal my y. And if y is 13, then what will be x? 21 over 13 times 13, so x is 21. Have I lost anyone? Whereabout? When I need to add fractions together, I have to make them to be the common denominator. And if I want to make a whole number to a fraction, such as 1, because y is 1y, that means whatever fraction I want to change it into, the numerator and the denominator have to be exactly the same. So that's why I can rewrite y as 13 over 13y, because that's again cancels down to 1. And then the next step that I can do, when I'm adding fractions together, obviously the denominator is not changing, because just because you have got more slices of the pizza, it's not going to change the size of each of the slices. So 21 plus 13 gives you 34. Okay? And then what I can do next, multiply by the 13 and divide them by the 34. So basically, 13 times 34 equals 34y, and then I can cancel them by the 34, so 13 equals 34 over 34y. That's why y is equal to 13. Okay? Was there anything else that was A bit too fast or confusing? It's quite funny that you get to the point when you can do complicated differentiations, but the fractions still scare people and strip up.
It's just being able to like, because I get the feeling that if I was doing this on my own, I would look at that, I'd look at 34 equals 21 over 13 y plus y, and I'd be like, where do I do that? And it's just intuitive thinking. Y is also 13 over 13 y, that all like breaks down.
Tony's been doing that quite a lot recently with lectures. He's like, and you can see that. And it's like, well, the
Like
only
me,
reason
yeah.
I can see it, but when I'm looking at it, I don't see it.
I think it's just,
Yeah, it's years of practice. I probably wouldn't be as fast at it if I was in your shoes, but I don't even want to think about how long I've been doing this. That makes me depressed. Okay, right. Yeah, so those are the optimal solutions, and obviously we don't go into the second order condition because that's a little bit complicated. Okay, now that was a nice and easy x and y's, but again, you need to be able to solve these in the realm of economics. And brace yourself for the algebra, because I deliberately chosen an example that is not necessarily the simplest. Okay, so what we got here? What kind of optimization problem is this?
That should be saying from two goods, right?
Could be. Yeah.
From two goods.
Yeah. Okay.
So what was your question?
So what kind of problem do we have here?
Maximize the utility given the budget.
Exactly. So we need to maximize the utility with a given budget constraint. So what is the utility that we need to maximize? Alpha ln x plus beta ln y. So that's my utility function. And I know that both alpha and beta are positive. And what is my constraint? Okay, I've chosen pxx and pyy. I could have chosen P1 and P2, no difference. Okay, so what am I going to do? Again, I need to build up the Lagrangian. So what will be the Lagrangian in this case? Okay, and then from here on, I just need to look at the first of the conditions. So the Lagrangian with respect to x, the Lagrangian with respect to y, and the Lagrangian with respect to lambda. Oh, by the way, what we have not identified in the previous question, we solved x and y, but what did we not find? We didn't find the value for lambda. Okay, so I don't know how often Tony is expecting you to find the value of lambda. Be sure that you don't lose it out if it's a question, because you will lose points. Okay, so we can always start with this one, because that's always the obvious, just gives you back the constraint. And then, what's the derivative with respect to x? That's not lambda. Alpha. Alpha over x. And that has to be equal to 0. The other one is with respect to y, so that will be beta over y minus lambda py, and that has to be equal to 0. So what are you going to do with these equations then? We obviously want to find optimal values for x and y. I have got 3 equations, 3 variables. I want to reduce the number of equations and reduce the number of variables so I can solve the equation simpler.
Move the lambda to the right hand side and then divide by the other.
So if I see that lambda is in both of them, and I can just simply express it as alpha over x equals lambda px, and beta over y equals lambda py, then I see if I divided them, that would eliminate lambda. So alpha over x over beta over y equals lambda px over lambda py, which is quite handy because the lambda goes. Now how do you divide 2 fractions? Flip the bottom and multiply it. So it's alpha over x times y over beta, and that is equals to px over py. And from here, now I can either express x or y. I'm probably going to express y because that is the simpler in here, because that's already on the top. So y will be equal to beta px over alpha py times x. Okay, so divide them by alpha, multiply alpha by beta, and multiply it by x as well. So I've got y as a function of everything, including x as well. What are you going to do next? Which equation have we not used yet? The third one. And the third, thankfully, only have got x and y. So I can substitute it back and then solve it. So m equals pxx plus pyy, and now I can substitute the y for this. What can I see? P5 cancels. So what I've got here is m equals pxx plus beta over alpha, pxx. So I want to express x as a function of m, px, and the rest of it.
Pxx.
Yeah, you said factor out. Sorry, I didn't.
Yeah.
I was wondering, what did he mean? I cannot catch that word.
Oh, sorry.
Okay, yes, we can factor out the pxx. So what's left behind from this term? 1. And from this term is beta over alpha. Now, I'm going to need that one, so we'll write it here. Y equals beta px over alpha pyx. So, when I look at this one, can I make it more like one fraction? And again, remembering that 1 is always numerator same as denominator, and the denominator here is alpha, I can rewrite this and furthermore And now I can do multiplications and divisions a little bit easier, because what I want is x. So I want x, I need to divide them by px. I need to multiply it by alpha and divide them by the alpha plus beta. And that gives me x star. If I wanted to write it all in one fraction, that will be alpha m over alpha plus beta times px. Or px times alpha plus beta, makes no difference.
So when you want alpha, when you solve for y, could I cross multiply the left hand side and solve for y that way? Like, you know, alpha beta xy equals px over py. It was on the right, but you rubbed it off.
This is the final one, because I will still need it.
Yeah.
I'm not sure what you. I mean, whatever I expressed in here, y or x, it's my choice. So I could have expressed x as a function of y and substitute that back into here and find the other variable. It doesn't matter which one you choose. The solution will be exactly the same, if that's what you meant. So just go whichever you fancy. Makes no difference. So that's x star now, but I want y star as well. And I'm going to need more space. So y is equals beta px over alpha py times x, which I found now, alpha m over alpha plus beta times px. Okay, so what can I see now? I can cancel. What can I cancel? So y star is equal to beta m over alpha plus beta py. Okay, and again, if you look at y star and x star, what can you see? Yes, so they've got their own prices and alpha changes to beta. So again, there is some sort of symmetry going on in here.
So where did you get for y? Where did both those things come from?
That was my y expressed as a function of x. Yeah, and I just substituted back x into there. So that was somewhere on here in the board a minute ago before I crossed it out. If I wanted to, I could still find the value of lambda. Obviously it's not on the board anymore, but I could go back into one of the original equations which still have got the lambda in there, substitute x and y back into that and find the value for lambda as well. I don't know, again, I can't remember now how often you need to find the value of lambda. Just remember that might be another question. Is everybody happy with this? I mean, as soon as you omit the numbers for letters, they start to become a little bit more daunting, but the algebra is the same. You just have to keep those blooming letters flying around. I mean, if it was numbers, I would have been able to calculate this value exactly, and then I wouldn't have to have these things. I probably would end up with something like 2 over 3 or similar. And I just have to keep the sums and the multiples and divisions. Okay, one more question in there. Find the indirect utility function. So what is the indirect utility function? Yes, so instead of the quantities that we want to buy, you express utility as the function of prices and incomes. So what you need to do here and I stupidly just got rid of my x star. Okay, so that was alpha m over alpha plus beta px. Okay, so what I need to do now, just pick up x star and y star and substitute that back into here. So, and you usually put that u star, is that correct? So that is alpha times the log of okay? What next?
Just leave it.
Yes, you can just leave it. I'm going to go into a little bit of algebra to show you what else you can do with it.
Factor out.
Would you make n the subject?
Hmm?
Would you make n make n the subject of the equation?
No. I just need to express u as the function of mpx and py. So this is actually a function here. But I just want to see it a little bit better what's going on. So I'm just going to do a little bit of algebraic manipulation. You want to double check with Tony how much he wants you to do anything about it. Okay, so what I've got here, alpha log mass, beta log mass. But I've got two logs added together. So if I could remove alpha and beta from the way, I can bring them together into one log. So what I can do first is bring the alpha as a power, and same for the beta. Into the power. And now they are not in my way. I've got single logs added together, so I can just multiply everything together. So that would be ln multiplied together now I've got alpha to the power of alpha, and I've got beta to the power of beta. And what else I've got? I've got m to the power of alpha and m to the power of beta. That will be m to the power of alpha plus beta. So that is in my numerator. What's going on in the denominator? I've got alpha plus beta to the power of alpha, and got the same alpha plus beta to the power of beta. So there is alpha plus beta to the power of alpha plus beta. And I've got px to the power of alpha and py to the power of beta. And I'm going to do a little bit of moving around, just a tiny little. And then I have got alpha over px, which both to the power of alpha. And I've got beta, beta over py, which both raised to the beta power. And I've got m over alpha plus beta, which both raised to the alpha plus beta power. And in this way, I might just see the relationship between the prices and the incomes a little bit clearer. Not necessarily.
In the rare case, when asked to find the indirect expenditure function? Can we just leave it in the first? Like
Indirect utility. I don't think you will need to be going into a lot of algebraic manipulations in here, but double check that with Tony what sort of form he wants you to get these ones.
You will have to go through that if you want to find the indirect expenditure.
I mean, it's exactly the same. That's the indirect expenditure function here, and that's the same function expressed in a slightly different way. It's the same function.
That's the indirect utility.
Yes. You can't find the indirect expenditure in here because that's not the objective function. So if you find the indirect expenditure, you had to do the other optimization problem.
Can I multiply the alpha m to, without putting the raised index?
They are two different index. Okay, what do you want to multiply together?
Now we'll do log of alpha m divided by alpha plus beta px multiply beta n.
No, because they are different powers.
Yeah, without raising the power to the.
That's what I'm saying. It would be something like to the squared and something like to the cubed. So you can't just multiply them together and raise them to the 2 plus 3 power.
Yeah, no, my point was the step above.
Oh, in here?
Yeah.
No, I can't, because the log rule is only telling me that ln x plus ln y equals ln xy. So there can't be anything in between. So that's why I had to remove the powers first. Otherwise, I can't bring them into a one log sign. Okay. Marshallian demand functions. So Marshallian or ordinary demand function comes when you maximizing utility subject to the budget constraint. Basically exactly what we've done before, but the utility now is slightly different, simpler than it was before. So my utility x1 to the 1/3 and x2 to the 2/3. And my budget constraint is P1x1 plus P2x2. So same budget constraint, slightly different notation. So find the Marshallian demand function by maximizing utility subject to the budget constraint of M. And then we need to again find the indirect utility. So the way that I can distinguish between Marshallian and Hicksian is I know that the Marshallian have to be a function of M and P. Marshallian for M. That's the only way I can remember. And then I will know, so that's my MDF. And I know that therefore the Hicksian has to be the other one, which will be the U and the P. That's the only way I can remember. You probably can remember it some other ways. So how are we going to start the problem solving process?
Quickly, so where you put the budget constraint in the brackets with lambda, you'd replace it for HDF with the utility function? Where
Yes.
would go?
Yes. So basically, I would sweep them. Yeah. This would be my objective function, and this would be the U minus after the bracket with lambda. We're going to go through that as well in the next. Just so you see exactly for the same function what's the difference between the two solution methods. So we are the Lagrangian. So what will be the Lagrangian for my case? And then I need to find lambda 1, lambda 2, not lambda, L1, L2, and L lambda. L lambda is basically just this. That is always your constraint. And L1, so differentiate this with respect to x1, bring the third down to the minus 2/3, x2 to the 2/3 doesn't change, minus p1 lambda, because there is an x1 there as well. That has to be equal to 0. When I do the differentiating with respect to x2, now I need to bring the power of x2 down, which is now 2/3. x1 doesn't change, and x2's power will be minus 1/3. And in the constraint there is x2 as well, so that's minus p2 lambda, have to be equal to 0. And what I'm going to do now is just rearrange these two and divide. Can I do that in one step? I think you're quite used to it now, right? So 1/3 x1 to the minus 2/3 x2 to the 2/3 over 2/3 x1 to the 1/3 x2 to the minus 1/3 equals p1 lambda over p2 lambda. Lambda cancels out. The third cancels out. So what do I have? What power do I have for x1? What's the power of x2? And what else do I have? So this is basic, and that equals p1 over p2. So this is basically x2 over 2x1. That is equal to p1 over p2. So obvious choice to express x2, because that's the least manipulation. So I'm going to write that here so I don't lose it. So x2 is 2 p1 x1 over p2. And then I can substitute this back into the third equation, or rather the rearranged version of the third equation. Can I rub the board? So m equals p1 x1 plus p2 x2, which is 2 p1 x1 over p2. p2 cancels. So m is equal p1 x1 plus 2 p1 x1. So m is equal 3 p1 x1. So x1 star is equals m over 3 p1. So that's my first Marshallian demand function. I need the second as well. I can come back into here. I'm not sure if that's going to be showing off the camera. So, is that all right if I take the top of this one? Yes?
I know that we have to substitute that first x2 value back into the constraint, but I don't understand why.
Because if I substitute it back into either of these, I still have lambda. And that's an extra variable, so I did not do away with the variable. So I would still have either x1 or x2 and the lambda. So I could still not solve it from here. So that's why I always go back to the third one, because that's the only one which has got just 2 variables, of one of which I already know.
So it's blinding obvious thing, but I've literally just realised that this L1, L2, L lambda thing is just a big simultaneous equation.
Yes.
Yeah. And you just make it make sense, you just get rid of the lambda straight away.
Exactly, because you have got 3 equations with 3 variables. You get rid of one of the variables, break it down into 2 equations, 2 variables, and then solve it that way. Glad something clicked today. Okay, I need to move this, because I need space. So this is my x2. That is equals 2p1 over p2 times the x1, which is this one. Actually, I don't need the bracket. Which is m over 3p1. So what I can do now, cancel out by the p1. And then x2 star is 2m over 3p2. And that is mdf2. Okay, so we got the Marshallian or ordinary demand functions, but we also need the indirect utility. So what you're going to do for that one? Yes, so you go back to the ordinary utility function, the original one, and you express this as a function of the m and p. To the 1/3, and what was, sorry, 2m over 3p2 to the 2/3. And I know that for these ones you do have to do a little bit of simplification, because it does make sense to get it done. So I've got m to the 1/3, 3 to the 1/3, p1 to the 1/3. I've got 2 to the 2/3, m to the 2/3, 3 to the 2/3, and p2 to the 2/3. So there's no other 2, so 2 to the 2/3 stays. But what will be the power of m? 1, because a third plus 2/3 makes it a 1. What will be the power of 3? 1 again. And p1 to the 1/3 and p2 to the 2/3. And that's your indirect utility.
If we're asked to find the expenditure function, will we just sort of make m, like rearrange that, cancel it out?
From this, yes, I can find the indirect. I can find the expenditure function as a function of utility price 1 and price 2, just rearranging it. We'll come to that in a minute. Okay, so we've got the Marshallian demand functions and we've got the indirect utility. Any questions?
But why is it called the indirect utility?
Because you can't get the utility directly from quantities. You can get it from indirectly from prices and incomes.
Michael wrote a very nice system of equations. So if you wanted to write the indirect utility function, it would be like u bracket m p1 p2. Is that right? If you wanted to write, like, if you wanted to describe what the indirect utility function was describing in the terms of
this was made.
Yeah.
It means that.
Yeah. Yeah, but you probably want to put here is indirect expenditure. Okay, so feel free to share that with anyone who's interested.
You say indirect because you cannot get the right from.
It's indirect. Okay, this is the direct utility because you can get the utility directly from just knowing the numbers of the products that you want. And it's indirect because you need to find the income and the price. You need to know the incomes and the prices to be able to find the utility. Okay? Same functions, different question. So, find the Hicksian demand function by minimizing the income required to achieve a given level of utility. So what happened in here now by posing the question this way? So now this is my constraint, and this is my objective function. So what will the Lagrangian look like in this case? Okay, so the difference here will be the build-up of the Lagrangian. The process will be exactly the same, but because the build-up of the Lagrangian is a little bit different, the equations themselves will be different. So the first of the conditions again, L1 is P1 minus 1/3 lambda x1 to the minus 2/3 x2 to the 2/3 being equal 0. L2 is P2 minus 2/3 lambda x1 to the 1/3 x2 to the minus 1/3, and that has to be equal to 0. And L lambda is just the constraint. And again, I pick up the first two equations, reduce the variables in there by cancelling the lambda out. So in that way, I end up with two equations, both of them only having x1 and x2. And then I can solve it as a system that way. So P1 over P2 equals 1/3 lambda x1 to the minus 2/3 x2 to the 2/3 over 2/3 lambda x1 to the 1/3 x2 to the minus 1/3. Cancel out lambda, cancel out 3. So I've got P1 over P2 equals 1/2. What's the power of x1? And the power of x2 is positive 1. So again, P1 over P2 equals x2 over 2x1. And again, it's easier to express x2. And I'm going to write it here because I will need it later on, so I don't want to accidentally erase it. So that will be 2P1 x1 over P2. So far, it's exactly the same. The equations look slightly different, but they're giving me the same. The difference here again will come from that I need to substitute back into the last equation now, because that's the only one which only has got x1 and x2. Can I rub this off? Is that all right? So u equals x1 to the 1/3 to p1 x1 over p2 to the 2/3. So u equals x1 to the 1/3, 2 to the 2/3, p1 to the 2/3, x1 to the 2/3 over p1 to the 2/3. So u equals, what is the power of x1? Ah, yes. What's the power of x1? That's handy. So what I'm going to do now is just express x1. So x1 equals u, multiply it by p2 to the 2/3, divide down by 2 to the 2/3 and p1 to the 2/3. And that is my Higgs-ian demand function for x1. And now I need to substitute that back into x2. Bless you. So x2 equals 2p1 over p2 times, I actually don't need the bracket, u p2 to the 2/3 over 2 to the 2/3 p1 to the 2/3. So, what can I see? I mean, u is not going to change. But I've got 2, 1 here, 2 to the power of 1 here, and 2 to the power of 2/3 down here. So what will be the power of 2? So I dealt with the 2's. Actually, I'm not going to cross that out there because that's just going to confuse people. So I dealt with the 2. The next in line is P1. P1 is here and P1 to the 2/3 is here. So what will be the overall power of P1? And now I still have to deal with P2. Is P2 coming up or is it going to stay down? It's going to stay down because the power of P2 at the bottom is bigger than the power of P2 at the top. And what will be the power of P2? 1/3 again. So I'm just going to write that up in a little neater way. So that will be 2 to the 1/3 p to the 1/3 u over p2 to the 1/3, and that is my Higgs-ian for x2.
In a question asking a Higgs-ian after the Marshallian, is it the utilities is going to be the same as it was in the Marshallian case?
I have chosen examples deliberately being the same.
But they can be different.
They can be different.
If they're the same, am I right in saying the other way of finding this would be using taking the derivative like Shepherd's lemma, like.
Yes, those are again Shepherd's lemma's Roy's identity again helping you if you're using the same utility and budget constraints.
Because I guess you'd save time as opposed to.
Exactly. It takes a long time. Yes, if they are the same. But I just wanted to show you the difference between this. Well, not so much of this.
The same, we have the choice to use whichever.
Yes, exactly, and you obviously want to use the shortcut.
Yeah. Sorry, can you repeat that? The shortcut.
I always forget which one's which, but it's either Roy's identity or Shepherd's lemma. I'm not an economist, so I don't even try to go and understand those. I just know that those helping you with shortcuts. So you go out, you go back home, read up on them, make sure that you understand, and then you use them. Okay, one last question is find the indirect expenditure function. So I need these two. And what will be my indirect expenditure function then? So m star will p1x1 plus p2x2, so that's m. M star will be p1 u p2 to the 2/3 over 2 to the 2/3 p1 to the 2/3 plus p2 times x2 star, which is 2 to the 1/3 p to the 1/3 u over p2 to the 1/3. So what can I do here? So I've got P1 up and P1 down, so that's going to give me P1 to the 1/3, P2 to the 2/3 U over 2 to the 2/3 plus I've got P2 up and P1 to the 1/3 down, so that gives me P2 to the 2/3, P1 to the 1/3 U and 2 to the 1/3. And that's it. What can I factor out? And what's left? Now, I don't know if you go back in your pages, and we were saying that because we use the same budget constraint and utility functions, budget function and utility function, oh, the solution is not here, damn it. From this function and the indirect utility that we found a couple of pages ago, they would have to be looking the same. I should be able to rearrange from one to the other. But at the moment, it doesn't look like it. So, because this is in my way. That is just not what is in the other function. So I need to rearrange that and to find out if I can actually end up with exactly the same function. So, I've got 1 to the 2/3, which is a fraction, and I have to add a number to it. So again, what I need to do, I need to bring them to the common denominator. And the common denominator here would be 2 to the 2/3. So 1 over 2 to the 2/3 will not change, but I'm going to multiply this by 2 to the 2/3 over 2 to the 2/3 So that would be the same denominator. And that's quite handy, because what does it give me? 2 to the 2/3 times 2 to the 1/3, that is just 2. So m star equals p1 to the 1/3, p2 to the 2/3 u times 1 plus 2 over 2 to the 2/3. So m star finally, 1 plus 2 is just giving me 3. So 3 p1 to the 1/3, p2 to the 2/3 u over 2 to the 2/3. And now, I think it's on the next slide actually. Yeah. So this is my m star, this was my u star, and you see that you can rearrange one to the other and you would find whichever function you would need. That only works because I used exactly the same constraint and the exactly same utility function. So as soon as you're changing one or the other, it's a different question. And I think I've got nothing else for today. Good.